Okay, so welcome to Tuesday. We are going to get an introduction to the binomial and geometric distribution using our M&Ms. All right, so we are going to pretend that these bags that I bought of M&Ms are somewhat a random sample of all the M&Ms produced by there's only two plants that produce these. One is in Cleveland, Ohio, and the other one is in Hackettstown, New Jersey. So all that I bought, go figure, being just right outside of Cleveland, these were all produced in Cleveland. So we're going to take our M&Ms and open up the plastic bag and dump them into the cup. And I know your cups are clear, but I have faith that you can do this as randomly as possible. Binomial means two. So like true, false, left, right, blue or not blue. So you can turn any situation really into a binomial situation, doing an event and its complement. So we're going to pretend that the blue M&Ms are defective, and we're going to see how many blue M&Ms we have. And we're going to do this using sampling. So what you need to do, and you're going to do this 5 times, you need to shake up your M&Ms in your cup, put your hand on the top, and then very carefully pull out 10 M&Ms. You don't want to pull out too many. So when you're getting close to 10, like you don't want to have to randomly decide what to put back. So my first sample, I had 3 out of the 10 M&Ms be blue. Now I'm going to put all of those back in the cup, and I'm going to shake it up really good and do it again. And you don't want to look at what you're pulling out. Oh, got to put them back in first. Huh? Did what? You don't have to put that one back in. It will be okay. It'll still be valid for our purposes. And Lily and the rest of you can make your draft after we get everybody's results. So after you do the 5 samples, what I want you to do next is pour them all out, count how many total you have, and also count how many blue ones you have and how many red ones you have. So I need to know the total M&Ms. I need to know the blue. And I need to know the red. Make sure you include the blue and the red in the total. I'm just saying that because that was something that a couple people forgot earlier today. Had a little plastic baggie. Could lay them on that. The only person that's touched that is me. Oh, that's kind of what I wanted, I guess. Oh, it's Cleveland, Tennessee. All right. So, if you are close to the windows, you can start doing the chapter or the C problems. But first, you need to see what you're going to be asked to do when the time comes. So, Lily, could you please read me the 5 numbers you got in your 5 samples?
I had 2 all 5 times.
Pardon?
I got 2 like all 5 times.
Like that?
Yeah.
All right. Adam, what did you get?
3, 2, 2.
All right. And then Henry?
What? Oh, 1, 4, 5, 4, 3.
And so that's what you guys will be asked to do here in a minute. These other total things I don't want for a bit. So Rowan?
2, 2, 2, and 3. Oh, it's another 2 in there.
Okay. And Jimmy?
2, 2, 5, 3, 3.
Okay. So you guys can just, I'll get you 3 here in just a second. Let me put these up before I get too confused. Okay, so that's 5, 2. So that's, I'm going to need these. And then 3 plus another. And then twos are winning. Okay, the 1, 2 fours, 5, and 1. 3 goes up to there. And I have 1, 2, 3, 4 twos. So 1, 2, 3, 4, and then 3 goes up to 3. And then 2 more 3s, so that's 1, 2, 1, 5, and 2 twos. So 1, 2. All right, so the next 3 people, starting with Rachel.
2, 1, 2, 0. 2 more, 2, 2, 2. Sorry.
That's okay. Rachel?
1, 1, 3, 3, 3.
All right, and Tyler?
3, 3, 1, 2. Not 3, sorry.
Okay. That hasn't happened all day today until, it's okay, we're just special, Mrs. Garrett. We are special. That's for sure. Okay, Delaney, what did you get?
3, 6, 2, 3, 1.
And then we will have Marcus.
I got 2, 3, 1, 4, 2.
Rania.
2, 2, 2, 3, 3.
And Emma.
3, 1, 1, 2, 1.
Okay. So you guys, I'll tell you how to do this in a minute, but all you guys that already gave me the information, you guys don't have to pay attention to me for a little bit. You can be working on your other homework. Six. Okay. So now I'm going after the last 2 rows, so you have to be ready, Freddies. Okay, we'll start with Rachel.
1, 1, 3, 1, 3.
1, 1, 3, 1, 3. And
3, 1, 2, 2, 2.
I missed the last one.
3, 1, 2, 2, 2.
All right, Michael.
1, 2, 2, 3, 4.
Philip.
3, 2, 4, 2, 3.
And we have Lily already gave us, so Nick.
3, 1, 2, 3, 5.
All right. So So let me do these and then I will explain to y'all what you need to do. All right. Okay. So you can now put X's or columns. I'm going to tell you where the top of your column should stop. So basically you are starting at 0, even though there isn't a 0. And there should be a column that goes up to 2 there, which is the first hash mark because the Y's are going by 2's. So whatever you want to do, put X's or put a bar up to 2. The 1's go up to 18. The 2's go all the way up to 35. The 3's go up to 27. The 4's go up to 5. The 5's go up to 3. And the 6's go up to 1. And since there are 4, 7, 8, 8, 8 is 16, 17, 18 of us, and we each did this 5 times, I should have 90 things up there, so let's see if I do. Ooh, I have 91. Oh. Somebody else got a 0, right? That's okay. Huh? Yeah, I had a 0 too. So that there are 2 zeros. All right. Well, 91's okay. It's not going to be terrible. 2, 18, 35, 27, 5, 3, 1. All right. It's okay. It will still work out just fine.
So we just make a bar graph or?
Well, dot plot, bar graph, histogram, whatever you want to. But those should be, I put the numbers that should be at the tops of the different values. And what would you call this distribution? A little bit right skewed, perhaps?
Yeah.
Okay. All right. Does the observed distribution seem to follow the hypothesized binomial distribution determined by the binomial value p equal 0.207 according to the Cleveland plant? Well, I can't answer that question yet. But let me come down here and tell me what I would expect it to be. The expected value, I took out 10, and it is about 20% blue, and so that should equal 2.07 blue M&Ms. And does this seem to balance a little bit after 2, do you think? I would say it balances between 2 and 3, wouldn't you? We'll actually calculate that out in a moment, but usually statisticians don't know. But we'll play God here in a moment. And the formula for the standard deviation is 10 times 0.207 times 1 minus 20.7 cents, which would give me 79.3 cents, I believe. 0.793 if you subtract. And if I do that in my calculator, in the next couple days we're going to be finding out exactly where those formulas came from. 10 times 0.207 times 0.793 is 1.28. Approximately 1.28 candies. So this should balance at about 2.07 and then give or take 1.28. And so our balance point is definitely within there.
What's the standard deviation?
Oh, I'll move it down here. All right, so if we had 90, well, let's see, if we had, now we're going to put how many total M&Ms. So we're going to go around the room, but I have to sit down to do this because it takes a little more concentration. I have what we got block 2. So I'm going to come up here and add block 4 total candies, block 4 blue candies, and block 4 red candies. Okay, so I had 84 total, 14 blue and 13 red. And we'll start with Nick and go the other way around. So here's opportunities for you to work on those homework problems. I'm going to start over here with Mr. Nelson and then go back to Philip and all the way up to Rachel, Delaney, all the way back to Emma, over to Tyler, up to Rachel, over to, or that will be up to Lily, and then Adam back to Jimmy. So, Mr. Nelson, what did you get total?
89 total.
And how many blue?
18 blue and 24 red.
Woo! Lots of red. Okay, so who's next? Philip?
Are you skipping Layla?
Yes, because, oh, she can have M&Ms to eat, but she didn't have to do this. Did you grab M&Ms? Do you want some? Okay. And I would just put them back there, but these are precious M&Ms. We wouldn't want the Ziploc bag to open by mistake. So, all right. Philip, how many total did you
I
get?
had 78 in total.
Oh, you got ripped off.
Got ripped off.
Okay, 78, and how many blue?
19 blue.
And how many red? All right, so next person would be Michael.
85 total.
Okay.
21 blue and 11 red.
Walker.
85 total, 13 blue and 11 red.
Rachel.
85 total, 15 blue, and 14 red.
All right, over to Delaney.
74.
Oh, she got ripped off more than you, Philip.
19 blue and 5 red.
Marcus?
I got 89 total,
Ooh, he has to give some of his up. No, I'm just kidding.
22 blue, and 9 red.
9? And you said 5 red, right, Delaney?
Yeah.
Sounds like a football play. Okay, Rania, how many total?
81. And 24 blue. And 14 red.
Emma?
88 total. 18 blue and 12 red.
Tyler?
82 total,
82? Go ahead.
18 blue, and 9 red.
And then I think, I don't remember who's next, Hannah.
94.
94?
17 blue and 16 red.
Rachel?
I had 96 total.
Ooh, we know who to rob now.
14 blue and 50 red.
All right, Lily, your turn.
84 total.
Go ahead.
84.
Yep, and then how many blue?
17 blue and 11 red.
Thank you. After Adam, add them up. How many did he get? 94 total. 8. Henry!
93 total, 27 blue, and 9 red.
Rowan.
I had 81, 14, 20.
And Jimmy.
92 total, 22 blue,
Did you say 22 for blue? And 10. All right, so now I can go to calculate one variable statistics on V4T. How many total M&Ms were in this experiment? Kind of like we're pretending this is a population. The number of total M&Ms were 1,554. Somebody write that down, maybe 2 or 3 people, thank you. Now we're going to calculate how many of them were blue. So we're going to go get the list of blue. And then I'm going to put this all together after school. How many blue? 331. Somebody write that down. I can see if I have my skills left from the COVID era. What was this? What was the total? 155. Can you imagine teaching a lesson like that? Writing with the mouse? I know how to do it. I've done it too many times. I ain't ever want to do it again. All right. Stat, calculate the red.
Nice one, huh? Thanks, Phil.
B4R. And that is 227. Look at those twos. 7 has a little bit to be desired. Okay, so what can I do with this? Well, we can see how close our sample was. Granted, it's not a huge sample compared to all the M&Ms in the world, or all the M&Ms produced at the Cleveland plant even in an hour. This is pretty wimpy. But if I want to find out what is my proportion of blue M&Ms, 331 divided by 1554. That's the proportion of blue. And the proportion of red M&Ms, 227 divided by 1554. See how close we are coming to what they claim to be. 331 divided by 1554.2129. So this is 0.213. And it's supposed to be 0.207, so that's not terrible. And for red's supposed to be 131. That's what they claim at the Cleveland plant. Jeez. Ooh, there's a brown M&M on the floor. Guess I didn't have 84, but only 83. Nope. To the best of my knowledge, nothing nasty has ever happened on this floor. Back in the old building where I had my classroom, there was a couple nasty misses of people being sick and I remember it well because I was pregnant at the time, so that was like 25 years ago, 26 years ago. Okay, so what is 227 divided by 1554? 0.146. So that's not too far from what they claim. And that's just called sampling variability. All right. So, binomial can look like this. It usually has quite a steep peak. And the formulas that are used are right here. These formulas are on your sheet for the day you take the AP exam. So if you look at your green fluorescent sheet, which you don't have to do it right now, but right here in the middle of the first page are the top times the bottom that we were using last week. And then we have this new one for binomial, and there's another one for geometric that we're going to look at. Today we're not going to explain where those came from. That's for tomorrow and the next day. Now we're going to switch to a geometric situation, and after that you can then eat your M&Ms. So we are now going to look at page 19 that was not ripped out of your packet. You are amazing, Henry. Nobody is near as amazing as you. So now we're going to do a geometric situation. It's very, very similar to binomial. Okay, Philip, you don't have to eat those, but you do have to count with those. I have a lot more bags up here that you can have to eat.
Eat that. Phil, eat that. Pick them up the floor.
Lily, Philip just dumped all of his M&Ms on the floor, so that's probably
like a vacuum.
I just
Sorry.
Well, you have time to transfer while Philip's organizing his life.
I was wondering why it looked a little bit different.
That's why. So yeah, Philip, I still need you to use that batch to collect our data. Otherwise, our data will be tainted. We do not want tainted data. We have tainted M&Ms that don't want to be put into your stomach, but we don't want to taint the data. That's the most important thing here. Doesn't matter if Philip develops the, it did. No, I'm just kidding. It does matter. Yeah, don't eat those. Nobody eat those. Philip, you can have this bag to eat. Plus, weren't you like
I kind of got screwed.
shorted anyway?
I was the second week. So.
Yeah, well,
Did on purpose to get more.
that's right.
That's right.
Okay, ready? This is what we're going to do now. In between every one, you got to shake it up well, and don't look, and you're going to pull them out one at a time, and you're going to keep pulling them out until you get a red one. As soon as you get the red one, stop and count out how many M&Ms are there, including that red one. one at a time. Until is the key word.
Hey.
See if somebody can beat Mr. Tails. I'm not going to tell you what it was, because then we'll have somebody beat it on purpose. This is the longest streak I've had today. On 8, 9. All right, got my first one in.
Oh,
We're doing it again. And then you got to put them all back in and shake her up. Geez. Did not take me this long earlier today.
you're kidding, but
Ah, no, I got a lot of red ones in there. They're just hiding from my finger. Are you done already, Walker?
yeah.
Walker cheated. No, I'm just kidding.
I got it on my first try.
Well, that helps. Woo! Maybe the red ones are lighter and they're all good at the top. And I think they didn't have it on black. Right from the top. This is not helping. Woo! Yes, it is.
There also be a difference because your cup is like smaller that way and ours is bigger. So like we
Yeah, I don't know.
Send it.
What are you sending?
What? What?
I'm not going to be sending you any new M&Ms if you're sending.
I'm now what are you gonna do?
13, 14,
I'm gonna get it.
15, 16, 17, 18, 19, 20, 21. All right, you can start eating them after you have that information.
Do it, send it. More.
No, I don't think it's a wise decision to chug them all at once. You want me to?
I'm built on life.
You're welcome. Ooh, they went on the floor.
Yeah, it was a joke, it was a joke.
You can recycle these.
I'm gonna get a couple out of that.
just so you know. All right, so we're gonna go around the room again, but we'll start in the middle. Let me get mine on here first. There's more time for you to be doing your homework if you desire. All right, so now we're gonna start in the middle. Just a second. Actually, Lily will get you out of the way and then we'll go to Delaney's row. So Lily, tell me your 5 numbers.
10,
Okay, go ahead.
2,
Yep,
22,
yep,
3,
yep.
and 16.
All right. Okay, Delaney, just give me your 5 numbers.
5,
Go ahead.
33, 26, 2, and 22.
All right, 5, 33, right? And then give me the next 3. 22,
26,
and then what?
22.
Okay, behind Delaney is, let me think, don't say anything, it's Marcus. Are they small? Okay, give me all 5 of them at once.
4, 4, 6, 6, 13.
Okay, I can do that. All right, I think behind Marcus is Rania.
1, 4, 1, 2, 3.
I can remember that. 1, 4, 1, 2, 3. Emma?
7, 6, 1, 4, 3.
7, 6, 1, 4, 3. 7, 6, 1, 4, 3. All right, Mr. Whitmer Rich.
2, 9, 5, 6, 2.
2, oh, 2, 9, 5, 6, 2.
Yeah.
Okay, Michael.
2, 10, 3, 5, 2.
2, 10, 3, 5, 2. 2, 10, 3, 5, 2. All right, Walker.
5, 1, 8, 9, 1.
5, 1, 8, 9. Uno. Rachel.
13, 5, 1, 24, 5.
13, 5, 1, 24, and then 5. And Mr. Nelson.
2, 4, 3, 1, 12.
2, 4, 3, 1, 12. 2, 4, 3, 1, 12. All right, heading back towards Jimmy. What's your 5?
3, 14, 12, 8, 31.
3, 14, 12.
8, 31.
Yep. 3, 14, 12, 8. And you said 31? All right. Rowan.
8, 2, 2, 1, 7.
8, 2, 2, 1, 7. Henry?
11, 6, 13, 8, 11.
11, 6.
13, 8, 11.
Thank you. 13, 8. 11. All right. Hang on. I'm thinking. Adam. Go ahead. 3, 7. 3, 7, 1, 1, 1.
Yo. 3, 7, 1. Highly old skills.
All right. And now we're at Hannah.
Oh. 3, 6, 6, 4, 10.
3, 6, 6.
I go wash my hands. All right.
4, 10. Is that what you said, Hannah? The last two are 4, 10. Somebody was interrupting my thinking. Good, he's gone. Okay. Oh, I'm sorry. That should have been Rachel and then Hannah. My bad.
We got it.
Rachel?
I was saying it. It's Hannah. Okay, 15, 8, 13, 6, 1.
15, 8. 13. 6. And then 1.
Yes.
All right, Tyler. Okay, hang on. All right. 5, 3. Oh, that's 4. 3, 2, 2. Did I do mine? Pretty sure I did. Yep, I'm going with I did. All right, so this is a geometric distribution, and it is always severely skewed to the right. Because when you think about what's happening, geometric distribution should always be severely skewed to the right. Right? Right. Okay. Was the probability close? Let's see. The proportion of greens out of 1557 was what? 227? You got arrested for who?
The guy, with Mayday, the song,
Yeah.
he got arrested for murder.
227.
He killed his cousin.
146.
That should be the guy who's like, yeah, I just got killed by the guy who made whipped potato. That's a rough way to die. Like, come on.
Was it 227? Does anybody remember?
Yeah, it was.
Okay. So we're pretty close, fairly close for answer 3. How many should we expect? Well, let's see. Where would you think that this balances? Oh, you guys have to make this. So I will tell you where you should put the top. Ones should go all the way up to 12. 2 should go up to 13. 3s should go up to 8. 4s should go up to 7. 5 should go up to 7. 6s should go up to 8. 7s are at 3. 8s are at 5. 9s are at 2. 10s are at 3. 11s are at 2. 12s are at 3. 13s are at 4. 14s are at 1. 15s are at 1. 16s are at 2, and then we skip to 119, 121, 2 22s, a 24, a 26, a 28, a 31, and a 33. All right. So how do we come up with, for green, how many would we expect? Well, mu is equal to 1 over the 1.31, which is 1 divided by 0.131, and that is 7.6. We would expect in the long run that we would have to pull out 7.63 M&Ms before we get a red one. And this up here actually balances at 7.54 with the 4 repeating. So that's really close to what it theoretically should be. And what's the standard deviation for pulling out 7 in a row, give or take what? Well, that would be 1 minus 0.131 divided by 0.131 squared, and then square rooted. And if I do that in my calculator, I get 1 minus 0.131 close parentheses divided by 0.131 squared, and that is equal to, give or take, 7.11. Oh, 116. So exactly how and where we get those formulas we'll be talking about for the rest of the week. But we have a couple things I want you to notice right now. You have both of your sheets there. Look at the graphs. Look at this graph and look at the binomial graph. There's some things that should stand out that are different between them. What does the binomial graph have that the geometric graph does not? Yep. So I'm going to go to my binomial graph, back to our binomial graph, and I'm going to write some of these things down. So binomial distributions. Some things to notice. They can have a value of 0. You're allowed to have points at 0 in the binomial. They usually have a pretty tall peak. Tall peaks are common because I asked them to, Henry. Oh, I thought you said, why are you writing this down?
Yeah,
Teacher quotes. I don't know, you got room under the big M&Ms.
Well, yeah.
Okay.
I got you.
All right. The other thing you should know about binomial distributions is they can be left skewed, right skewed, or very bell-shaped. That's what the 10% condition and the large counts condition we're talking about last night in your notes. Binomials can camouflage very easily as a normal distribution. In fact, for the rest of inference, we need to know when they're camouflaged enough to call them normal. All right, that's about their distributions. Now let's look at the binomial formulas. N-O-M-I-A-L formulas. Which you don't have to write these down. I'm just writing them down because mine are way up there and yours, at least you can see them very quickly. How are those two formulas different than the geometric formulas? I can think of two ways that those two formulas are different than the two formulas that you have in number 4 for the geometric. Anybody? Yeah? Go ahead, Tyler. Yeah, it has an N, and it doesn't have any what? Divisions. There's no denominators like the geometric ones have denominators. So for these formulas, the things you have to notice is they use N, which is the number of sample size or trials. We took out 10 blue or 10 total M&Ms, and we did it 5 times. And we'll also put no denominators. Okay? Let's go talk about the geometric distributions. And Henry, you're going to have to put this all the way over at the right there somewhere, just in case you were worried about where you could put this.
Yeah.
What about geometric distributions? For geometric distributions, the lowest number is 1. No zeros. You can't go until if you never go. Right?
Right.
So it has to start at 1. And they are always, what? I told you this earlier. Always right skewed. Does that mean we say that the maximum is infinity? Like, could you stand here and keep pulling things out of your cup until forever? No. You would pull them out, like if you only had one red M&M in there, then it would be like a number 80 or something. So it's not infinity, I call it indefinite. We don't know how many trials we're doing, they're indefinite. They're not infinite, we just don't know, so they're indefinite. And what about the formula? The formulas, no N, because we don't know what N is, because we're going until. So the key word is until. You see that word, you know it's a geometric distribution. It's like if you see the word expected, you know it's a mean. All right. We are going to fill out some of page 20 and then we'll be done. And hopefully by this time, did everybody get those 4 problems done so you don't have any homework?
Yeah.
I'm hoping. That's what I'm hoping for. How you doing, Lily? Okay? We get to see you tomorrow. Woohoo! Okay. So, way back at the beginning of honor statistics, we introduced you to distributions. And distributions are just graphs. Like here's a distribution of how much sleep college statistics students got. It's just a graph. This is a dot plot. You could turn it into a bar or a chart or a histogram pretty easily. Here's a distribution of commute time minutes. That's actually very symmetric and it has a bell shape. So we can go through that flow chart. This is the percent of people in each state that were born outside of the United States. So these are foreign-born residents in each state. Ohio, this is a little bit old too, by the way. It's probably 5 to 10 years old. I don't know exactly. Ohio is at 3.6. So most of our residents are actually born in the United States of America. California, however, 27% almost 30% of their population that live in the state of California were not born in the United States. They were probably born in Mexico. If you're in California, if you're Florida, you think like Mexico or maybe Cuban. Also, probably Florida attracts people from more all over the place because it's warmer. All right, so those are regular distributions. So think in your mind, at the top of the chart is distributions. There are special distributions called probability distributions. And those come from random variables like we talked about the other day. I can graph this as a regular distribution, but if I turn this frequency into relative frequency, any idea what happens to that graph? If I turn the y scale into relative frequency, it's exactly the same. So the only way that I know that this is a probability distribution is if you tell me that it came from a random variable. So some distributions are probability distributions. Some probability, and we have the top times the bottom dance thing for the expected value, and we have the each value minus the mean squared times the probability to find the standard deviation. So those are shortcuts. If you know your distribution is a probability distribution, there's kind of some shortcuts you can take to find the mean and the standard deviation. And if you're lucky enough to find out that your probability distribution, and I think we did this, didn't we, at the very end of Friday? Put these on our, okay. If you're lucky enough to find out that your probability distribution is actually a binomial distribution, then there's even shorter shortcuts. And that's where we are at right now. So we're kind of nested underneath distributions, probability distributions. A special type of probability distribution is a binomial distribution. And that's what we're looking at. So we are on page 20. The Census Bureau reports that 27% of California residents are foreign-born. Plus, this problem just makes me happy because it's fun to say foreign-born. Foreign-born. Suppose that you choose 3 Californians, independent, so not in the same family, because that would, create more dependency. There are 8 possible arrangements of foreign and domestic birth. For example, FFD means foreign-born, foreign-born, domestic. So we have FFF, and then we could have FFD, and then we could have FDF, and then we could have DFF. That's all the way that you could have 2 foreign-born and 1 domestic. And then we could have FDD, or we could have DFD, or we could have DDF for only 1 foreign-born, or we could have all 3 born in the United States, DDD. So what we are going to do is take a regular probability distribution and show you how it connects to the binomial, and that will take today and tomorrow. But right now we're going to calculate these probabilities. If foreign-born is 0.27, the top one is 0.27 times itself 3 times. What's 1 minus 0.27? 0.73. So this one is going to be 0.27 times 0.27 times 0.73. And this one's going to be 0.27, and then the 3 moves in the middle, and then it ends with a 0.27. And here the 0.73 starts, and guess what? All of those 3 are going to have in common.
Final probability.
Yep, they're going to be the same answer, right? Because it's called the commutative property of multiplication. So all of these 3 should have the same answer. Now how about this one? 0.27 times 0.73 times 0.73. Move that 0.27 to the middle. And then finally move it to the end. And all of those should be equal as well. And then for the last one, we have 0.73 times 0.73 times 0.73. And I am going to select the following peeps. All right. The top one is going to be Marcus. Please find out what 0.27 times itself 3 times is. And then Mr. Nelson, can you do the next one? 2 foreign-borns and a domestic. Philip, you are selected to do 2 domestics and a foreign-born. And Hannah gets the 3 domestics. And 3 people are going to be given the task of tallying this all up. Emma, Rowan, and Delaney. So as they give us the results, you need to add them up. And then we'll be done here in a minute. Jeez Louise. It's not like we have an AP test in May or something.
Yeah.
Okay, so I think it was Marcus. What'd you get for the 0.27 to the third?
0.019683.
And I do want all the decimal pieces parts, please. And I think that is all the decimal pieces parts. Okay, Nick, what'd you get for the next one?
0.053217.
And we have that 3 times. And then we have Philip.
0.143883.
And finally, Hannah.
0.38901.
And I would like Emma, Rowan, and Delaney, after you get those all tallied up, I want you to hold up on your hands your answer. Let me know what you got, Emma. Yep, it should be, and all 3 of them got the number 1, because that's what a probability distribution should always add up to. So tomorrow we're going to graph that and turn it into a probability distribution by adding up the 1F, the 2F, and the 3F. And so you don't really have any homework because you already did it all. Woohoo! All right, Lily, you're welcome to go whenever you want. We'll see you in person tomorrow. All is good. You're welcome to take the little baggie of M&Ms with you if you haven't finished. Please recycle your plastic cups and have a phenomenal sunny afternoon. Yep, thank you. Did one of the, Rania, did you tell me about Mrs. Kramer having that? Yeah, I found mine.
I like it.
Yep.
I'm excited.
I want to make one for the smart board, so that's my next task. You guys have a great afternoon.